Have you ever stopped to think about the hidden science that shapes literally everything around us? I mean, from the phone in your hand to the air you're breathing. It's all run by chemistry. It's this incredibly powerful force that's completely invisible, but it's everywhere. So let's pull back the curtain and take a look.
This is a story that really cuts both ways. We're going to see how understanding the tiniest, most fundamental particles lets us build incredible new things, but also how ignoring that same science can lead to, well, absolute disaster.
This is the scene of a real tragedy. March 16th, 1994. It's 7:30 in the morning and a huge beam on a bridge that's under construction just gives way. It crashes down onto the road below. 3 people were killed.
So you have to ask, what on earth went wrong? Was it a mistake in the design? Did someone mess up the engineering calculations? Well, the real answer is something much, much smaller, and honestly, a lot sneakier than that.
It turns out the culprit wasn't one single event. It was a slow, silent chemical process, corrosion. You see, it wasn't a sudden break, but a gradual decay happening from the inside out. In this case, chemistry was this destructive force, just eating away at the bridge's supports until they finally failed. But here's the thing about chemistry, right? For every destructive process like corrosion, there's a creative one waiting to be discovered. Once you understand the fundamental rules of the game, you can switch from just preventing problems to actually engineering brand new possibilities. We can go from the kind of chemistry that causes pollution to the kind that creates clean, green energy. It's wild to think that the same science that explains how things fall apart is also the key to building a much better, more sustainable future.
And this isn't just theory. This is the science driving some of the most exciting frontiers out there right now. We're talking about shrinking technology down to the nanoscale, creating smart materials that can basically think for themselves, and developing things like those flexible screens you're starting to see. It all comes down to one thing: being able to control matter.
And this isn't sci-fi, it's actually incredibly practical. I mean, take this window. It's got this special coating that uses sunlight to break down dirt, and then the rain just washes it all away. That window on the left hasn't been cleaned in 6 months. That's the power of smart materials in our everyday lives.
Or what about this? This isn't just a piece of plastic wrap. That's an electronic circuit. The chemistry of conductive polymers lets us build electronics that are not only super thin and see-through, but also totally flexible. This is the kind of stuff that makes foldable phones and wearable medical sensors possible.
So, how is any of this even possible? To get that, we need to go smaller. I mean, way smaller. We need to look at the fundamental building blocks of all the stuff we call matter.
It all starts with the atom. The ancient Greeks actually came up with the name atomos, which literally means indivisible, because they figured it had to be the smallest possible piece of anything. They were on the right track, for sure, but they weren't quite right. I mean, when you look at the timeline, it's pretty amazing. It took over 2,000 years of discoveries to really peel back the layers. From those early ideas to finding the electron, then the proton, then the nucleus at the center, and finally the neutron, our picture of this indivisible particle got a whole lot more complex and way more interesting.
And so this is the basic model we work with today. You've got this dense little core in the middle, that's the nucleus, and it's surrounded by this cloud of electrons zipping around it. The properties of literally everything in the universe are decided by what's going on inside these tiny, tiny structures.
So inside the atom, there are really 3 key players. In that nucleus, you've got your positive protons and your neutral neutrons. They make up pretty much all the weight. But then orbiting that core, you have the negative electrons. And these guys, they are the real movers and shakers. They're the ones that decide how an atom is going to interact with everything else.
Okay, so we know what atoms are, but they're impossibly tiny. You can't just, pick one up and put it on a scale. So how do chemists actually work with them? How in the world do you count something you literally can't even see?
This is the huge challenge, right? If you want to build something like self-cleaning glass or a flexible screen, you need to have the right number of the right kinds of atoms. So how do you connect that invisible, microscopic world with the real, tangible world of a science lab?
The answer is a number. And it's not just any number. It is a truly mind-bogglingly enormous number. It's called Avogadro's number, and it is the secret key that unlocks all of modern chemistry. Just to try and wrap your head around how big this number is, get this. If you had that many marbles, what we call a mole of marbles, they would cover the entire surface of the Earth in a layer 65 kilometers thick. That's about 40 miles. It's a scale that's just almost impossible to imagine. So what is this number? Well, chemists call this specific quantity a mole. And honestly, the absolute easiest way to think about it is, it's like a dozen. You know a dozen is always 12 of something? Well, a mole is always Avogadro's number of particles. It's just a counting unit that acts like a magic bridge connecting the invisible world of atomic mass to the grams we can actually weigh out in a lab.
And this picture shows the idea perfectly. Every single one of these beakers contains exactly 1 mole of a substance. That means they all have the exact same number of particles inside. But just look at them. Because the individual atoms and molecules all have different weights, a mole of each one looks totally different. This is it. This is how chemists can count atoms just by weighing them. It's brilliant.
So let's put it all together. We have the building blocks, the atoms, and now we have a tool to count them, the mole. When you put those two things together, that's when you get real power. Because if you can count your ingredients, you can write a recipe. And in chemistry, that recipe is the blueprint for matter itself.
And when chemists write these blueprints, they usually use 2 main types. The empirical formula, that gives you the simplest ratio of atoms. For glucose, that's CH2O. But the molecular formula, that's the one that gives you the actual number of atoms in a single molecule, C6H12O6. Both are useful, but only the molecular formula shows you the true final structure.
And this brings us right back to where we started. By understanding this blueprint, the atoms, how to count them, and how they all fit together, we can do so much more than just figure out why a bridge might collapse. We get the power to design and create the world that we actually want to live in.
From the smallest, unseen particles to our biggest, grandest achievements, it really all comes down to this fundamental science. We have the blueprint in our hands, so the only question left is, what are we going to build with it next?